Okay, so good evening and welcome to the sixth live session for applied linear algebra for signal processing, data analytics, and machine learning. And today we'll be covering some sample problems and based on the contents of week number 6. So the videos are available in the course web page. And by the way, those who don't know me, a brief introduction about myself. So my name is Avik Mukhopadhyay, and I'm a PhD research scholar at the Department of Electrical Engineering at IIT Madras. So I'm one of the TAs for this course. So every Fridays we'll have this weekly live sessions from 6 to 8 p.m. So this is the sixth session, as I said, and in week number 6, if you recall the lectures, mainly the topics revolved around the least norm solution. So in the previous week we have seen least square solution, or the least squares fit or approximation. Its counterpart, so to speak, is the least norm method, right? And depending on the nature of the matrix, that coefficient matrix in the system, we either go for the least squares method or least norm method. And particularly we have seen that whenever the matrix in question is a wide matrix or a fat matrix where we have more number of columns than the number of rows, then we go for the least norm solution. In fact, we have, I think, seen some problems in the previous week as well, but never mind, we will solve one or two questions today also. And then we also saw the scenario of multi-user beamformer system, right, where there were like two antennas, two users, particularly two users at the transmitter end, with one antenna each, and then the receiver had multiple, let's say L number of antennas, and out of the two antennas or two systems at the transmitter end, one was our desired signal and the other one was the interferer. So of course we wanted to maximize the gain from the desired signal and suppress the gain of the interferer, and that's where beamforming technique comes into the picture, and we saw how we can do that. And we actually saw what's the beamformer, the vector that's required for optimization, optimal signal to noise and signal to interference and noise ratio, right? The optimal beamformer is one that maximizes the SINR. So we looked at its mathematical expression, and then also we looked at SVD, right? It's an important technique. It stands for singular value decomposition. So any matrix, and it applies to any matrix. So unlike the eigenvalue decomposition, which holds for square matrices, SVD is applicable to any matrix. So you can factorize them, any matrix, into a product of three matrices of the form U times sigma times V Hermitian. I'm sticking to the notation that was used in the class. So, and where U, sigma, and V, they have their own set of properties. U was a semi-unitary matrix, meaning that U Hermitian times U is equal to identity. That must be satisfied, and that sigma happens to be a diagonal matrix, if you remember, with the diagonal entries as the singular values of the matrix that we are factorizing. So, and those diagonal entries are arranged in the decreasing order or descending order. As we go from top to bottom, the values decrease. That was how it was arranged. And the third matrix, which was that V Hermitian part, that happens to be an n cross n. It's a square matrix and it's unitary actually, meaning that V Hermitian V is equals to V Hermitian equals to identity. So although this factorization is not unique, I mean, I would say this whatever factorization was discussed in the lectures is more closely related to the what is known as compact SVD, sometimes known as, but you can come up with a different factorization as well. So where this sometimes this nature of this U, V, sigma matrices are sometimes different. So yeah, but I'll stick to the method that was discussed in the lectures, where, as I said, what is v, what is u, what is v, and what is sigma, what should be their properties. Okay, so and also we saw an application where SVT is used, and we do something called the pre-coding at the transmitter. We have a MIMO system, and one of the problems is the coupling, where we have the interference from the other transmitted symbols, meaning that yi is affected at a time instant I, it is affected by the other symbols also from the input. But so that's coupling, some kind of a coupling, right? So multiple inputs are affecting the output at a particular time instant. But in order to eliminate that, we can use this pre-coding technique, SVD technique, combining at the receiver, and come up with a decoupled system. We looked at that. So once the system is decoupled, the output yi is only dependent on xi and not on any other xj's. Okay, so let's then begin today's session by keeping these concepts in mind. So I mean, the course name is a bit big, but I'm just sticking to applied linear algebra. Okay, so this is week 6, and I should be precise. I mean, this is not week 6 but session 6, which in which we will discuss the contents from week 6. So the first one, let's begin with the first question. Okay, so yeah, so read the question and feel free to respond if you have any thoughts how to approach it. There's nothing fancy about it, it's just known formula, that's it. So we are given a system of equation like y bar equals to a times x bar, and you have a as the coefficient matrix that's given to you. It's a 2 cross 4 matrix, and the vector y bar is given, it's a 2 cross 1 vector. So the unknown quantity here is that x bar vector. So what is the least norm solution for this system of equations? Okay, what's the least norm solution for the unknown x bar vector is what has been asked in the question. So if you carefully see, as I said before, we are asked about least norm solution, which makes sense because here we have, if you observe the matrix A, it has 2 rows whereas it has 4 columns. So it's a wide matrix, right? So, and whenever there is a wide matrix, we go for the least norm solution, which we have seen in the week 6 lectures. But had it been a tall matrix in which there are more rows than columns, then we would have gone for the least square solution. And you can obviously guess that for the case of a square matrix, both essentially are the same. I mean, least norm, least squares, both are the same. Okay, so so, and we know, we have seen the formula for least norm solution, how it's given. So we'll simply solve for that. Okay. Okay, and feel free to interrupt me if there is any doubt, anything is not clear. Okay. So the system is basically y bar equals to a x bar, where your matrix A is given by -1, -1, 1, -1, -1, 1, 1, 1, and your vector y is 4 2. Okay, so what is the dimension of the vector x? What should be the size of x here? Yeah, you have y bar equals to ax bar. For it to make sense dimensionally, so you know A is 2 cross 4, right? This is 2 cross 4. This is 2 cross 4 matrix. Yeah, someone wants to say anything?
Will it be 4 is 4 into 1?
Yeah, exactly, 4 cross 1. Because on the right, on the left side, we have y bar, which is a 2 cross 1 vector. So this is 2 cross 1. A is 2 cross 4. So what is the dimension of x? So it's clearly 4 cross 1, right? Because in general, if you have some C equals to A times B, where let's say C, A and B are matrices, I mean a vector can also be thought as a special case of a matrix, right? Where we have a single column. Just a second. So here, if A is of size, let's say m cross n, then I can multiply B on the right side of A only if B has n number of rows. So these two must be matching. Okay, these two must be matching. That's my condition. So B should be some n cross, let's say P. So then only this multiplication will make sense, and the resultant matrix after multiplication, let me call it C, that would be of dimension m cross P. So you can imagine like this n and n gets cancelled as if, and we are left with m cross P. Okay, so it's the same idea that we have used here, and we can, you know, observe that x should be clearly 4 cross 1. So x is my unknown vector. So let me, you know, call x to be this vector. Let's say there should be 4 unknowns, right? It's a 4 cross 1. So let me label them as x1, x2, x3, x4. Okay, I don't know what is this. So this I'm wanting to get a solution for this x bar, and particularly the least norm solution for x bar. And A, as you can see from the structure itself, it's a wide matrix. Why a wide matrix? Because it has more columns than the rows. And if you actually form the system of equations, if you want to write it in an equation form, this is expressed in a matrix form, y equals to ax. But if you actually expand and write in terms of the unknowns, what can you say? So how many equations will be there? There will be 2 equations, right? There are 2 rows of this matrix. So the first equation will be, so I have a x bar equals to y bar. So this is my a, right? I'm just writing this intermediate steps just for, you know, completeness. I can skip them. Okay, so this is my 4 minus 4. So I will have 2 equations in 4 unknowns. So if I form the equations, the first equation would be, I'll take the inner product of this first row of A and the only column of x. So I'll get x1 minus x1 plus x2 minus x3 plus x4 is equal to minus 4. That's my first equation. And similarly, if I compute the second row, so that will be minus x1 minus x2 plus x3 plus x4, and that's equal to 2, correct? So what do I have? I have two equations in 4 unknowns. x1, x2, x3, x4 are my unknowns. So clearly my number of equations is less than number of unknowns. So my number of equations is less than number of unknowns, and such a system of linear equations has got a name.
Dependent.
No, not dependent, it's called an underdetermined system.
Okay.
So here it's 2 and this is 4, so underdetermined system. It makes sense, right? Because we have less equations in hand but more unknowns. So I mean, it's not, clearly deterministic. It's not, we are unable to determine it clearly, so there is a gap, so underdetermined. But on the other side, if we have more equations in hand with less unknowns, then we have like more than enough requirement. So it's like that is known as overdetermined system, okay, when we have more equations than the number of unknowns. So this is an underdetermined system of linear equations, and whenever we have such an underdetermined system, we go for least norm solution, okay. And once you observe this A matrix and you see that it's a wide matrix having more columns than rows, clearly you can conclude that it's an underdetermined system, and straight away you can go for the least norm solution. So therefore the least norm solution is given by x bar. I am using this subscript ln just to denote least norm, and we have seen in the lectures, actually you can verify later. So that's given by the coefficient matrix which was a Hermitian, okay, times a Hermitian the whole inverse times y bar. And what is Hermitian? It is the transpose conjugate. So you take the complex conjugate of all the entries of the matrix and also take the transpose of the matrix. Doesn't matter in which sequence you do, you either take the transpose first and the conjugate next, or vice versa, okay. So that's the Hermitian. So H is Hermitian, which is the transpose conjugate. So I have I think mentioned this in the last session as well. So I mean, there are different notations used in different places. Some people use dagger notation, some people use just star. So yeah, okay. But in our case, the matrix, all the things you see are real, right? The matrix A is a purely real matrix. All the entries are real numbers. So the complex conjugate part doesn't make any difference. So Hermitian is same as doing just the transpose, right? I mean, the conjugate is just redundant, it won't have any effect. So I can clearly write this as, I can replace the Hermitian by transpose. The Hermitian is a more general case which applies to a complex matrix, but in our case we have a real matrix, okay. So now let's solve this. How can I write this? Because A is real here in our question. So now let's solve it one by one, so part by part. So A transpose is something which we need to find. So what is A transpose? A is given as this 2 cross 4 matrix. So I will write it down. this matrix. And so just tell me what will be A transpose.
So 4 rows, 2 columns.
4 rows, 2 columns. Okay,
-1, 1, -1, 1, first column.
right,
And -1, -1, 1, 1.
good. So yeah, it's simply the exchanging the rows and columns. So okay, so now this is a 2 cross 4 and this is a 4 cross 2, so the resultant would be a 2 cross 2 matrix, and we know how to multiply matrices hopefully. And if you actually compute this, you will find this is equal to 4004, so which is the same as 4 times your identity matrix, right? 2 cross 2 identity matrix. So this is 4 times identity, and in the expression of the least norm solution we have to take its inverse as well. So this inverse, and we have particularly seen this type of a problem in our last week as well, last session as well. So can you quickly tell me, like, what will be the inverse of this matrix? Exactly. So this is a diagonal matrix, right? And whenever we have a diagonal matrix, taking its inverse is just simple. I mean, you have to have its diagonal entries as some non-zero entries for sure. We can simply just replace the diagonal entries by their reciprocals, and that's it. Off diagonal elements are anyway 0. Okay, so this is nothing but your identity by 4. Okay, now okay, let me go to the next page. Now once again I'm writing the expression for the least norm solution. That was this thing. Okay, so A transpose, this is A transpose times this whole inverse we just calculated. It is identity by 4 times y bar, so that is the same as 1/4 A transpose y bar. And I already have the knowledge of A and y bar, so I'll just substitute for them, and what I will find is -4 2. Okay. So this thing, actually this part is what we are calculating, right? This this thing, this is actually also the right pseudo inverse of A, because if you multiply this whole thing, let's say this whole thing, you call it some A prime. If you multiply this A prime to the right of A, you will actually get identity. Okay, so although I mean this is behaving as a right inverse of A. So yeah, we have seen this, we have seen these terminologies in the last week as well. Okay, so this is the thing. And okay, now on calculating this, you will get this. Okay, so this is your least norm solution for mean, and why it is known as least norm, because I mean it takes the norm of the distance and minimizes it. Okay, that y bar minus ax bar, that norm squared is minimized. So this is the solution, and if you check with the options, it is matching with option D. So the answer is option D. Okay. Any questions so far? Let me check. Okay, then let's move on to the next one. Okay, so I think I can make it larger. Okay, yeah.
Actually, I just wanted to know which is this assignment question paper you are saying, because week 6 is this is not the one, right?
I didn't understand.
You are picking these questions randomly, or you are picking it from somewhere else?
No, I am creating some sample problems that are based on the
Okay.
contents that were
Okay.
covered in week 6.
Okay. Fine.
So I am actually going parallelly with the weeks. So in the course web page, you already have this week 6 videos available, and as you see, these are the topics, right? This polynomial fitting list norm, multi-user beamforming, SVD, all that I revised, I mean, in the beginning of the session. So my contents are based on this, but I am ensuring that the it's not matching with the current assignments, because that's something which you will be graded,
Yes.
right? So
Okay. Okay.
yeah. So these are some sample problems which are, hopefully, I mean, the purpose is to give you some idea so that you can uh, solve the current assignments. So yeah. Okay, so all right, so this is a scenario of multi-user beamforming. Okay, um, yeah, and this is the scenario that in fact was discussed in the lectures also. Like I said, at the transmitter we have two users, right? One is a desired user and the other is an interfering user. And at the receiver there are like multiple antennas. In this case there are 4 antennas. So that's a MIMO system, and you are given the desired user channel vector, which is denoted by h bar, and of course it should be a 4x1 vector. Why? Because at the receiver there are 4 antennas, and from that transmitter antenna of the desired user we have 4 such links, right? 4 such channel coefficients. And similarly from the interfering user antenna we have 4 such links or 4 such coefficients to the 4 receiving antennas. And similarly this we will obtain g bar as well, which is given, which is the vector for the interferer channel. So given this information, you are asked to find the optimal beamforming, and for this also you need to revisit the lectures. So beamforming is a method which, as I said, is trying to maximize the signal to interference plus noise ratio. So as the name suggests, a beam is formed that tries to maximize the gain from the desired users and suppress the gain for the interfering users. That's the strategy. So yeah, and we have looked at the maths of it in the lectures. I think professor has described everything, and it has this optimal beamformer is also a vector w bar, which has a mathematical formulation. So the idea, as I said, so there will be three parts. Okay, there will be three parts. One is the signal component, then we have the noise component, and we have the interference component. So we set some constraints. We maximize the signal component and suppress the interference and the noise component. And we saw, I mean, how it can be the W bar vector, which is the beamformer, how the optimal beamformer can be expressed in the form of a matrix.
Sir,
Yeah,
I have a doubt. Noise and interference, they are two different entities.
yeah, they are actually, I mean, although they might sound similar, but in this setting they are two different entities.
Okay, okay. Thank you, sir.
Yeah, so that's why in the uh, terminology also we use signal to interference and noise ratio, SINR. There is something called SNR, that's fine, where we are not considering any interference, but we can also have noise as well as interference. So there are two different things.
Okay, sir. Thank you.
Okay, so mm, so in this question, basically my interferer part is the second user. As I have mentioned in the question, at the transmitter end I have two users. One of them is my desired user and the other one is my interfering user. Okay, and whenever there is an interfering user or an interference, so called, I want to provide my maximum signal quality to my desirable user and suppress the gain for the interfering user. And noise is something like it's always there whenever there is a channel. I mean, the most general channel that we consider is the AWGN channel, right, additive wide Gaussian noise channel, so which is modeled as a Gaussian random distribution. So that's always present. So in any normal simple, the simplest of systems, if you consider let's say some y bar equals to x bar plus n, that n is your noise vector, that's always present. That's yeah, so that is the noise vector. So that's not coming from this interfering user. Okay, so yeah, so I think once I draw the picture, I think it will be clear. And I mean, these definitions can be, they depend on the context actually. If you are analyzing a wireless communication system, let's say there is a cell tower base station and there are certain surrounding neighboring cells. In there also we have certain interfering cells, and interference is also further could be classified into different categories like O channel interference and so on. So yeah, intracellular, intercellular and so on. But noise also, again, it has many different types of noise are there. Thermal noise, and AWGN noise, pink noise, many types of noise are there. So yeah, but the idea is, as you said, yeah, both are different. And in this case the setup is like this. So this is the transmitter side where I have, let's say, user 1, and this is my desired user. This is and there is another user which is user 2. This is my interfering user. So this user 2 is my source of interference, which is not the same as noise. And so this is at the transmitter side, right? And each of them has one transmitting antenna like this. And on the receiver side, so this is the transmitter, okay, this is the transmitter. On the receiver side, so TX stands for transmitter and RX stands for receiver. Let me anyways just write it down, transmitter, and this is the receiver. Okay, at the receiver, as per the question, you have 4 antennas. Okay, and of course there will be links, right? From the user 1, from the antenna of user 1, this can be one link to the receive antenna 1. Similarly, from the user 1's antenna, there could be another link to the second receiving antenna, to the third receiving antenna, and similarly to the fourth receiving antenna. And these links have some, channel coefficient. So you can think each link to be some, channel. Let's say the entire actually space between the transmitter and receiver is a channel, but these are some elements of the channel, you can say. Okay, and which will be actually the elements of the channel vector, as you will see. So the first link forms the first channel coefficient between the user 1's antenna and the first receiving antenna, this link. So this is my H1. Okay, similarly, from user 1's antenna to the second receiving antenna, the channel coefficient will be H2. This is H3 and this is H4. Similarly, there will be such links from the user 2's antenna as well, which is my interferer. So if I use some other color, let's say this, this, like this. Okay, so here my coefficients would be G1, G2, G3 and G4. So what are these H1, H2, G1, G2? So Hi in general, Hi is the channel coefficient. Channel coefficient between desired user, which is user 1 as per the diagram, and receive antenna ith receiving antenna. Okay, and Gi is the similarly the channel coefficient between interfering user, which is user 2 as per our diagram, and receive antenna I. Okay, and now once you have these channel coefficients, you can form a vector by choosing the elements of the vector as these coefficients. So the channel vector H bar, which is actually given in our question, this is nothing but H1, H2, H3 and H4. Okay, this is actually given. This is the desired user channel vector, right? Because my HIs are the coefficients from the desired user and the receiving antennas. So this h bar, this is my desired user channel vector. Okay, and this is given in the question actually. The elements are, the vector is this, and it will be 4x1, right, because there are 4 such links, since there are 4 receiving antennas. And G bar, what is G bar then? G bar is my interfering user channel vector. So that will be G1, G2, G3, G4. And that is also given as 3152. So, and as I said, we are asked to find the optimal beamformer. So a beamformer will actually do something like this, I mean, it will try to form a beam which is directed more towards the desired user, which is user 1 in our case. So like this green, and it will try to suppress the gain for the second user, which is the interferer. And just a second. So I'm not going into the theory actually, because we have seen actually the main key point to remember is that the optimal beamformer is chosen such that it maximizes the signal to interference plus noise ratio, or SINR, maximizes the SINR. So the signal part is in the numerator and the interference and the noise part is in the denominator. So you want to enhance or increase the numerator, which is the signal strength, and you want to suppress or decrease the interference part and the noise part, which is at the denominator. Or in other words, you want to increase the SINR, this ratio. So what we have seen from the lectures, so I'll just make a note here, recall lecture 28. In 28th lecture we have actually seen this mathematical formulation that the optimal, so that's, as I said, that optimal beamformer is actually a vector, and the notation that we used was W bar, and that is also chosen, like it's actually a combination, weighted combination of your received signals, and that is chosen such that your SINR is optimal, the best. For that you give maximum gain for the desired user and suppress the gains for the interferers and the noise. And I think in the analysis that was done in the class, for that the desired signal gain was set to 1, equal to 1. The interference gain was set to 0, so it had no component at all. And with that yeah, so let me just cross check one thing. This the setting was something like this. So there was this w bar vector, which was our optimal beamformer. So its inner product with the received vector y bar was given by three components, and y bar can further be expressed as sum of three terms. Y bar is a sum of three terms where we have h bar x1, so this is corresponding to the desired user, then g bar x2, this is corresponding to the interferer, and n bar, which is the noise. Okay, so and if you split this, it had like three components. Just I am splitting this summation. Okay, and this first part is the desired signal component, desired signal part. This is my interferer part, which is clearly visible, right? H bar, whenever there is H bar was that channel vector corresponding to the desired user, right? And G bar corresponded to the channel vector for the interferer. So this is the interfering part, or the interference, and this is my noise component, because n bar is my noise. This was the notation that was used in the lectures, if you recall, lecture 28. So as you can see, the terms are clearly different, right? These are two different components. Interference and noise are two different components, they are not the same. And what we did was we set this portion. So so the coefficient of x1 is this w bar Hermitian h bar, right? This coefficient, this is the coefficient of x1. So that's the gain of the desired signal. That is the gain of the desired signal, and we had set this to 0. Sorry, set this to 1, because we want to set it at maximum gain for the desired signal. And similarly for the gain of the interference, which is w bar Hermitian g bar, we wanted to suppress it, therefore we had set that gain to 0. And once we did that, so this I can also rewrite this as h bar Hermitian w bar equals to 1, and I can also write this as g bar Hermitian w bar equals to 0. And then what we did was we put them in a matrix form like this: h bar g bar Hermitian w bar is equal to this 1 0, right? And okay, so this is where this 1 and 0 is coming for. Okay, the noise is intrinsically present, right? This noise component will be present. Okay, this is what the beamformer is doing. It is setting the gain, it is maximizing the gain, setting it to 1 for the desired part, and suppressing the effect of the interference by setting the gain for the interferer to be 0. Okay, so and this and this was denoted by some C Hermitian matrix, and what we got was this C Hermitian w bar equals to 1 0, where the matrix C was basically formed by taking the two different channel vectors, h bar and g bar. So, and we saw that this will be a system which will again be a underdetermined system, because this C matrix is actually in our case it is a 4x2 matrix, so anyways it will be a tall matrix. So C Hermitian would be a wide matrix which has more columns than rows. So C is a tall matrix, right? And C Hermitian is a wide matrix, right? And a wide matrix times some vector equals to some vector is, again, whenever there is wide matrix, the solution is the least norm solution. Remember the first problem that we discussed? So the solution for y bar is given by the least norm solution, and that was given by basically your w bar w bar C into C Hermitian C whole inverse this y vector. This was the solution. Okay, so I wrote the how this came. Actually, I gave you a brief overview of how this came, and this quantity here w bar, this quantity here w bar is your, what is the optimal, right? Optimal multi-user beamforming. Okay, so this is the, we are setting, so this was my desired signal gain, which was set to 1. Desired signal gain, and this was my interferer gain, which we wanted to suppress, and hence we set to 0. Okay, that's the job of the beamformer, and ultimately we arrived at this form, which is our optimal beamformer. So where, again I'll write where my C is nothing but this matrix H bar G bar. Now in our question we have everything. In our question the H bar and G bar are given, right? These two vectors. So I can form the matrix C using H bar and C bar. Okay, so what will it look like? So H bar is nothing but 1 2 4 1, and G bar is nothing but 3 1 5 2. And all we need to now do is just find this whole, solve for W bar. That's it. So let's do it part by part. So C Hermitian C is something which we need to find first, and then take its inverse. So C Hermitian C, again it's the same as C transpose C because it's a real matrix in this case. So how do you find this? It's simply this product. Okay, and if you do the math, you will get this matrix. Okay, it's a 2 cross 2 matrix. So far fortunately we have dealt with only 2 cross 2 matrices, and we want to find its inverse as well. So for 2 cross 2 matrix, inverse is pretty straightforward. So how do we find the inverse? We take the adjugate and divide by the determinant. So the determinant of, what's the determinant of this matrix here? How do you find the determinant of a 2 cross 2 matrix? Yeah, this is the 2 cross 2 matrix.
So 22 into 39 minus 27 squared.
Exactly.
39 minus
Yeah. So you basically multiply these diagonal elements together and then subtract the product of the off diagonal elements, which is 27 and 27. So once you do that, so that will be the value of the determinant, and this inverse will exist only if that determinant is non-zero. And for non-zero determinants, the matrices are known as non-singular, because we are dividing by the determinant, right, to find the inverse. If that determinant itself is 0, then the inverse is undefined, so it doesn't exist. So the determinant is, as you rightly said, this is this quantity, it's in the denominator, and then we have the adjugate, sometimes it's also known as the adjoint. So that is, for a 2 cross 2 matrix is pretty simple. The strategy is like, okay, you consider the diagonal entries, right? So first diagonal entry 1 comma 1 entry is 22. So which element is sitting directly diagonally opposite to 22? It's 39. So you replace 22 by its diagonally opposite element, which is 39, like this. So basically you swap this 22 and 39, and 22 now comes at this place. So you swap these two diagonal elements, and you also swap the off diagonal elements, but with a flipped sign, with a negative sign. So meaning that, I mean, if you have let's say A, B, C, D, and also at the end you take the transpose, don't forget that. So if you have a matrix A, B, C, D, right, let's say A, then A inverse is nothing but you take the determinant, right, and divide by the determinant, so that is AD minus BC. That's done. Maybe I'll just so this is just rough, you know. So okay, so this is I think it was C, Hermitian C. Okay, so yeah, so here, as I was saying, A inverse would be, you first divide by the determinant AD minus BC, and you swap these diagonal elements with no change of sign, so D and A, right, and you also swap the off diagonal elements. So here initially there was B, now it becomes C, but with a negative sign. And similarly here it was C, but you replace C by its diagonal component, which is minus B, but remember this negative sign. And finally you take the transpose, so this is 1 by AD minus BC, D minus C minus B A. Okay, so this is simple, and this is exactly what we are doing here. So here what you have is, if you find this determinant, it is actually 129, right, and here you will have this matrix, and you just need to complete the remaining calculations. So remember, this was our form for W bar. I mean, this 1 0, this is like the ideal scenario which we want, right? I mean, maximizing the gain equal to 1 for the desired signal, and just entirely suppressing the gain for the interferer, which is set to 0. Okay, but it could be some 0, like 0.95 and 0.05, whatever, but this is like the perfect scenario. Okay, so now C, we know what is C. And this inverse we just calculated, and we have 1 0. Okay, and it's just a matter of calculation, you know. So I'm just writing the final answer. This vector is my optimal beamforming. And it turns out that the correct answer is option A. So any questions for this? How we did the calculation and all? This is a 2-user scenario. 2 users at the transmitter, out of which one is the desired one and the other one is the interferer one, and noise is definitely present in the channel, right? So, and particularly the noise is an additive noise here, it's a noise vector. This, you see, there are 3 components: desired signal, interference and noise. And the beamformer, what it does is it sets the gain, right? It maximizes the desired signal gain, it sets it to 1, it minimizes or suppresses the interferer gain, sets it to 0, and then we form a system of equations where the solution is given by the least norm solution, right? Because the C Hermitian matrix appears to be a wide matrix, and the least norm solution, so this whatever optimal multi-user beamformer solution I have actually written in the box, this is actually obtained by the least norm solution, right? And yeah, where the C is actually this matrix formed by taking the channel vectors for the desired signal and the interferer, right? We found C given, H bar and G bar were given, we found C, and then we just solved this entire equation, and this is what we obtained. Okay, if there are no questions, then I'll move to the third one. Okay, so now let's move to the third one. Yeah, okay, so this is again based on the singular value decomposition. This was one topic which was introduced in week 6 lectures. Okay, so if you haven't gone through the videos, I suggest you go through them. So you see that the matrix H is factorized. It has been expressed as a product of 3 matrices. The first one is a rectangular matrix 4 cross 2, the second one is a 2 cross 2 matrix, and the third one is another 2 cross 2 matrix. So we are asked what is the largest singular value typically denoted by sigma 1 of this H matrix. What is that? So yeah, go ahead. Yeah, can you repeat?
3.
Okay, it might tempt you to answer that it's 3. I think you are looking at this middle matrix, and
No,
you are
actually, I think we need to change that one also, because
right,
sir,
right,
he
right.
actually asked to change the rows and columns and
Correct, exactly. So just by the first glance it might appear that okay, I have this diagonal matrix where the entries are 2 and 3, and out of them
But
the
it is not
largest,
in descending order. That is why.
exactly. So but you see, this is not in the descending order. This is in the increasing order, right? We have
Yeah.
2 first and then 3.
Yeah.
So the first step that we, as you clearly pointed out, is to change this in a decreasing order or a descending order. And on top of that, the SVD decomposition which sir discussed had a particular form, U sigma and V Hermitian, where U was semi-unitary and V was unitary, and that middle matrix which was sigma, it's a diagonal matrix, and the diagonal entries are arranged in decreasing order and all of them are non-negative. That was the condition. So we have to somehow arrange the entire product of these three terms in that form. Then only we can say, okay, we can, once we arrive at that form, then we can choose the largest singular value and write, okay, what is sigma 1. Okay. Okay, so let's see how we can, do this. So the given matrix here, H, is this. So this is what is given. Okay, remember my goal is to express H in a form U sigma V Hermitian, where my U matrix is a semi-unitary matrix, where, meaning that U Hermitian U must be identity. Okay, I mean, in general, like if I talk about the dimensions, if H is m cross n, right, then U should be m cross n, sigma should be n cross n, and V Hermitian or as well as V both are n cross n. So overall you can verify that the dimension would be, for H it would be n cross n. Okay, and since U, as you see in this product, in this decomposition, is a rectangular matrix, so it is semi-unitary, meaning that it will satisfy, it has to satisfy U Hermitian U equals to identity, and particularly identity of n cross n size. Okay, so but this is not necessarily true, like it's also the other way, I mean in the other direction as well, which is U Hermitian. That's not true necessarily. Okay, that's why it's called semi-unitary and not completely fully unitary. Okay, so this is one constraint on U, and U is known as U is semi-unitary. Okay, and my sigma is a diagonal matrix, should be a diagonal matrix of this form. So you can, so it is a diagonal matrix, so only the diagonal entries will be non-zero. So sigma 1, sigma 2, all the way till sigma n, because it's an n cross n matrix, right? And all these off diagonal parts are 0. So I am writing a big 0, meaning that all the off diagonal elements are 0, right? Okay, and remember, they should be in decreasing order, like this, and all should be non-negative. And finally, what about V? V should be satisfying this condition, and since V is square, so it will be unitary, actually it's fully unitary. So V Hermitian V is equals to V Hermitian is identity. Okay, so V is unitary, and as I said, SVD is not necessarily unique. The factorization is not necessarily unique. So this is just one representation where I am choosing my U, sigma and V of this form. Okay. Okay. Um, yeah. So clearly, as someone said that this, if you compare with these conditions, my clearly my middle matrix here 2003, the diagonal entries are not in the decreasing order, right? So I first want to uh, make sure that they are in the decreasing order. So my observation is that this is not in decreasing order. Yeah, is there a question?
No, I was just trying to tell that no, we need to interchange the rows in the same.
Yes. So you see the idea here, as sir has also taught during the lectures. So so one strategy is that um, we have to play around with the rows and columns. So as sir showed you in the lectures, what he did was he exchanged the columns of this matrix, the first matrix. So I'm denoting it by this, it's like a column swap. Okay. And for the product to remain unchanged, since for this matrix I did a column swap, for its adjacent matrix I have to do a row swap. Okay, then only the product will be the same. So I am multiplying a rectangular matrix with a diagonal matrix, and you can actually verify that this indeed will, make sure that things are not changing. Let's say, I mean, how can I convince you? Let's say I am having a matrix like this. Okay, and let's say I am multiplying it with another matrix which is of this form, let's say E0 0 F. Okay, so what I am saying, so what can you expect in the product? It will be simply AE BF CE and DF, right? What I am saying is, if I interchange the columns here, I'll get BDSE, and if I interchange the rows here, I'll get 0F E0. Right, now if you take the product, what do you get? Again this will be AE, this will be BF, this is CE, and this is DF. Okay, so you see these two are same, right? So are you convinced that this is actually okay? We are fine.
Yeah.
Okay, so I'll just maybe let me just keep it only for reference. So that's what I am doing. Okay, that's what I'm doing. So once I do that, what will I get? Okay, I'm just exchanging the columns of the first matrix, so I'll get half half minus half minus half. This is half and half, right? And if I swap the rows for the middle matrix, I'll get this. And for the third, I am not doing anything as of now. Okay, now you still see, I mean, still we are not yet done. because my middle matrix has to be a diagonal matrix, right? But this is not a diagonal matrix. So to make it a diagonal matrix, what can we do is we can now actually swap the columns for this matrix, right? Because if we exchange the columns, then it will become, the first column becomes 3 0 and the second column becomes 0 2, and in that case it becomes a diagonal matrix, and also it ensures that the diagonal entries are sorted in the decreasing order, right? So what I will do is I will swap these two columns, and as I said, if you are swapping these two columns, what do you need to do here? Swap the rows, right? So that the product of these two remains unchanged. Okay, so sorry, I didn't mean to remove this. Okay, so I'm not writing what exactly in words what I'm doing, I'm just dictating. Okay, and so my h, now after doing that, I have three zero zero two, and you are swapping the rows for the third matrix, so you have this thing. Okay, okay, so now for the middle matrix we are in a safe zone, that okay, they are in the decreasing order and it's a diagonal matrix, but we also have to satisfy the conditions for the u and v Hermitian parts, the first and the third matrix. So although the u part, which is this first matrix, is actually in this case a semi-unitary matrix, you can actually check that if you call this as some u, you can actually check that u Hermitian u is indeed identity. You can actually check. So that's okay. That is met. But for this part here, this guy, this is not the V Hermitian that you want in the SVD, because for this you can actually verify that V Hermitian V is not actually identity, or neither is like V Hermitian. Okay, because if you take this as V Hermitian, so V is nothing but its transpose conjugate, which is this. So now, as I said, if you take V Hermitian V, what do you get? 1 1 2 minus 2, this Hermitian. So this would be 2 did I write it correctly? Okay, 2 0 0 8, right, if I have written it correctly. So this is clearly not identity, you see. So V is not meeting my requirement here, so I am still not in a right form. So this is not yet in my SVD form. So where is the okay. So usually you see here that my first row of this third matrix, the first row is 1 1, so it's okay. I mean 1 is always a it's easy to deal with, but here in the second row you have 2 and minus 2, 2 and minus 2, so 2 is a common factor, right? So you can somehow reduce this if you can divide this second row by 2, it gets simplified. So the second row then becomes 1 and minus 1, but you have to make sure that the overall product remains unchanged. Okay, so what I am saying you is I am taking this second row, this I am dividing this, dividing by 2. So I am basically normalizing it. But for the product to remain same, I should do some adjustments as well, right? So if I divide the second row by 2, for this part here, I have to take the second column and multiply it by 2. Okay, then only the product will remain the same. And if you are not convinced, again you can actually check for yourself that indeed this is actually true. And like I showed you before also, let me show you in a rough space here. So let's say again I'm using A, B, C, D, okay, and some, let's say, E, F, G, H. Okay, so what I am saying is I am dividing okay, I am dividing this. Okay, wait, so once you multiply this, what you get is AE plus BG, AF plus BH. Okay, so CE plus DG, CF plus DH, right? Now what I am saying is I am dividing the second row of the second matrix by 2, and to adjust for that I am multiplying the second column of the first matrix by 2. This, what is the result that you get here? AE plus PG, right? Because this 2 and half gets cancelled out, and this second term would be this, and this is CE plus DG, and similarly this is CF plus DH. You see, they are the same. So this makes sense. My product remains unchanged. So this is what I am doing. Okay. I mean this is something I did. You need not do it. I mean, ultimately your goal is to arrive at that U sigma V Hermitian form. Doesn't matter which sequence of steps you follow. Okay, but they must be valid. They must be like mathematically correct. Okay, so once you do that, what do you get? Just a second, I think So the first matrix remains the same, right? And the second matrix, the second column gets multiplied by 2, so it becomes this. And for the third matrix, the second row is divided by 2, so it becomes this. Okay, all right. But this creates a trouble for us, because initially you see the middle matrix was in the decreasing order, the diagonal elements were in decreasing order, but here by doing these operations, this sequence of steps, once again the diagonal elements are in the ascending order actually, but we don't want that. So for that again some exchange of rows and columns we need to do. So what I'll do is I'll swap the columns for this and I'll swap the rows for this, so that the product remains unchanged. So this is 4, this one. Okay, we are not yet arrived at the diagonal form, so for that one more step is needed, which is swapping of the columns. And if I swap the columns for this, I have to exchange the rows for this. So my H is now okay. So now I am in decreasing order, and this part is my U, it's valid because U Hermitian U is indeed, that will give you identity, you can actually verify that. And this is also my, appears to be my sigma, but still for this part this is not yet my V Hermitian, because if you choose this to be V Hermitian, what is my V? V is this, right? And what if you compute V Hermitian V, what do you get? You'll get 2002. So this is very close to our identity, it's basically 2 times identity. So all we, and you can indeed actually verify also the other way around, V times V Hermitian, that will be 1 1 minus 1 minus 1 and 1 minus 1 1 1. So that will be 2 0 0 and 2 again. So that's again 2 times identity. So we just are away from a scaling factor, that's it. So essentially what we need to do is normalize this matrix. Okay, so what do I mean by normalization? It's basically you check the columns, okay, you check the columns of the matrix and take its norm. So for this, what is the first column? This 1 1, right? And so what is the norm of this 1 1 vector? You simply do square root of 1 square plus 1 square, which is square root 2. So square root 2 is my normalization factor. I have to divide this by square root 2, right? I have to divide this entire matrix by square root 2. Okay, so because once you do that, then that matrix will be your valid V Hermitian, and you can actually check V Hermitian. V is equal to V Hermitian equals to identity. Okay, because I'll have a normalizing factor of square root 2, right? And as I multiply it 2 times, so 1 by square root 2 times 1 by square root 2 will give me a factor of 1 by 2, and in the previous case we came up with the product as 2 times identity, right? So this half will take care of that 2 times identity, and it will actually give me exactly identity. So root 2 is my normalizing factor needed. And for this first matrix, you can actually verify if you take the norm of the columns. If you take the norm of the columns, right? So this is clearly equal to 1. So it's already normalized. Okay, it's already unit norm. So just you have to normalize the columns, make them unit norm. And also, as you know, that they are kind of orthogonal and unit norm, so orthonormal, because they are properties of unitary matrices. So although this U is semi-unitary because it's rectangular, V has to be unitary because it's square. So the columns are clearly orthogonal, because if you take their inner product, it is 0, and they are also unit norm. So for that, what you are doing is normalize this. Okay, and how we normalize, we have seen. So the normalizing factor is square root 2. So this is already normalized. So no need of doing anything. So if we normalize this third vector, we have to divide by square root 2. So this is 1 by square root 2 minus 1 by square root 2, again 1 by square root 2, and 1 by square root 2. But to make the product unchanged, since I divided by square root 2, I have to multiply here by square root 2. Correct? So what I have done is adjust with a multiplicative with a suitable multiplicative factor. Okay, that's what I have done. So now this entire product, this decomposition, is indeed in my U sigma V Hermitian form, and you can actually check that U Hermitian U is indeed identity of 2 cross 2, right? M cross n, remember U is M cross n, so n is 2 here, so this identity must be n cross n, so it is 2 cross 2. And V Hermitian V is also V Hermitian is again 2 cross 2 identity, right? And my sigma is also in a form sigma 1 0 sigma 2, where sigma 1 is greater than or equals to sigma 2, which is greater than or equals to 0 in the non-decreasing order and with non-negative singular values. So we have expressed in the desired form. So now sigma 1 is 4 root 2, right, and sigma 2 is 3 root 2, but in the question we are asked to find the largest singular value. Okay, since they are arranged in the descending order, sigma 1 is the largest, so this here is the largest singular value of the matrix H. 4 root 2 is the right answer, which is option C. So my correct answer is option C. So is this clear? Are all the steps clear?
Yes, yes, yes.
Okay, okay. And just
Only one question in the previous, just last but one step where we divided it by root 2.
yes,
Yeah, and that one should be, we need to take the row value, or it should be for individual row. Here, incidentally, both are 1 minus 1, 1, 1. But if it were not 1 minus 1 and something else, then still it would be norm of that under root.
okay. So what you are asking is this about this third matrix.
Yes, yes, last one where we divided it by root, because we have taken it under root 1 square plus 1 square.
Yeah, so the idea is for the third matrix, as you know, in this particular form, we want that third matrix to be a unitary matrix. And for a unitary matrix, actually the rows or columns, whatever, they are orthonormal. That's one property. So orthonormal meaning that they are orthogonal as well as they should have unit norm. So clearly you can see that they are orthogonal, because if you take the inner product of either 1 1 with minus 1 1, inner product is 0. So they are orthogonal. And I mean it could have been some this also minus 2 2, let's say, then also it would have been orthogonal. And also we have to make sure that it is of unit norm. So these two individual vectors also need to be normalized for that. So
We have to do first vector by root 2 and the second by
yeah. So
8.
so the idea is that that's why I actually normalized that 2 minus 2 row previously. So that actually gave me a nice form with all entries as 1, just with
Yes.
a negative sign. But in this case, again, if you have to do, so if you normalize that, let's say 1 by root 2, 1 by root 2, and for the second column, what is the thing? It's like 4 plus 4, it's 2 root 2, right? So you have to divide by 2 root 2, so that is 1 by root 2.
And accordingly multiply the
Exactly, yes. So I'm just writing directly. So if you normalize that, you have to accordingly adjust for the uh, other matrices, so that the product remains unchanged.
rows.
So let's check. So if this is the case, if you normalize this like that, now these two column vectors are clearly orthogonal, as well as they have unit norms, so they are orthonormal. And if I label this as some matrix, let's say V, then what is my V Hermitian V? Let's check. My V Hermitian V is 1 by root 2 minus 1 by root 2, 1 by root 2 minus 1 by root 2, right? And this is thing. Okay, so this will actually half plus half, this is 1, this will be 0, this will be again 0, this is again 1. So this is indeed giving me identity. And you can do the other way also, it will give you. So essentially what I am doing here is I am dividing the first column by root 2, but the second column I am dividing by 2 root 2. So accordingly you have to adjust for its pre-multiplying matrix,
Yeah.
right? So
Yes.
yeah, you have to be a bit careful for that. So Yeah, so nice that you mentioned this. Yeah. Okay, so mm, okay. Uh, okay.
Here, when we say, okay, that was in the previous thing, maybe at the end I will ask that question because we will deviate from the flow.
Okay. So, all right. And now for the fourth question. Actually, the fourth question is also it's along the similar lines. It's a similar question only, except for we are asked to find the second largest singular value in this case. So, which is our sigma 2. So, yeah, once we convert that into the desired form, we have to pick sigma 2, not sigma 1. Okay, the second largest one. Only there will be two singular values, right? Sigma 1 and sigma 2. We have to pick the second largest one.
Yeah.
So okay, and I think the process now, I think it's clear and you can do that. So this time let me go it a bit faster. So this is 1 minus 1 minus 1 1 minus 1 minus 1 1 1, and this is 6005, and this is 2 minus 2 3 3. Okay, all right. So again, as you see, for this one, it appears to be in a very nice form, because again you see the columns are orthogonal actually, but they are not normalized. So normalization is not a big thing, we can do it later also. Basically in this case, the norm is, I think, 1 square plus 1 square plus 1 square plus 1 square, which is 2. So we have to divide by the 2. That's not a big deal. And their inner product, if you take the inner product of these two columns, it's simply minus 1 plus 1 plus 1, which is 0. So they are orthogonal. And the second matrix, it is in the sigma form, which is in the descending order. That's fine, but this guy is not in the V Hermitian form. It's not a unitary, right? So
Yes.
I mean, although its columns are no, it's not even orthogonal. You see, it's not even orthogonal, because if you take the inner product, it's minus 4 plus 9, which is not 0. So for this, again, as I did for the previous example, we had something like this form, right? 1 1 2 minus
Yes.
2. So I took this second row and normalized it. I mean, I divided by 2. So here also you see, you can divide the first row and second row by 2 and 3 respectively.
Right.
So what I'll do
Or
is,
you multiply in the first previous matrix.
exactly, yeah, so I have to adjust for those factors. So um, this, what I will do is, I will, okay, wait, something is, color is, yeah, I will divide by 2. Let me use some other color. Okay.
Divide by 2.
Divide by 3, and for that I also have to make some adjustments in the preceding matrix, which is, since I divided by 2 in the first row, so for the first column I have to multiply by 2, and for the second column I have to multiply by 3. So let me use the same colors, uh, the same colors, okay, and okay, this I will multiply by 3 and this I will multiply by 2. Okay, so the overall product remains unchanged, and once you do that,
Now again it is in descending.
yeah, you have to check that. So now it changed to the ascending order actually, which we don't want. So you see, I mean the diagonal elements are not in the decreasing order anymore. So this is what you get. So this is not in decreasing order. So for that again we do the same thing, we just swap the
Actually,
columns.
here
Yeah,
only when divided, we can normalize it also, right? So that would be one step.
okay, what you are saying is
The last matrix, because again we will see that it will not be normalized and we need to normalize.
that's true, that's true. I mean normalization is not a very challenging step. So the main thing is with this middle matrix. So
Okay.
yeah, so the sequence of steps is not unique. You can do something before, ultimately you have to arrive in the desired form, that's it. So you can follow a different sequence of steps. So yeah, that's perfectly fine. So make sure, but we have to make sure that at every step the product is not changing, the result is not changing. So yeah, so I will come to the normalization later.
Yeah.
So now I am doing the column swap for this first matrix, and for that I have to swap the rows for this second matrix. So doing that, I'll have and this becomes okay. Okay, and now to make it a diagonal matrix, I can do a column swap for this, and I'll do a row swap for the third matrix. Okay, so my H is minus 1 1 minus 1 1 1 minus 1 minus 1 1, and this is uh, this becomes this. Okay, now it's in the decreasing order, so fine. Now the only thing remaining is here is that, okay, for the third matrix the only thing required is normalization, because you see the column vectors are orthogonal, that is fine. And you can actually check that if you take this as V Hermitian, if you compute V Hermitian V, you will get something times identity, and that factor will be the normalization factor that you need to divide with. So in this case I think you will get square root 2 times identity. So
Right.
so so for both these matrices we need to normalize. And once you normalize it, you make the adjustment, adjust by suitable for the second matrix, suitable multiplicative factor. So clearly the normalization factors, they are visible. For this one it's actually 1 square plus 1 square, which is square root 2, and for the first matrix it's basically 1 square plus 1 square plus 1 square plus 1 square. I mean ignoring the negative sign because we are squaring them, so it's 2. Okay, so we have to divide the first matrix by 2 and the third matrix by root 2. So overall the dividing factor is 2 root 2, so we will have to multiply the middle matrix by 2 root 2. So
Yeah.
this is now in the normalized form, and I'll write it in the end. And this one will be okay. This one will be 1 by root 2, 1 by root 2, 1 by root 2 minus 1 by root 2. So the overall factor, normalization factor, is 2 root 2. So I have to multiply the middle matrix by 2 root 2, and so it becomes this. Okay, now everything is in my desirable form. So this is can be taken as my U matrix. This is my sigma matrix, which is in the decreasing order and non-negative, and this is my V Hermitian, and you can check that all my conditions are being satisfied, right? And V Hermitian V is equals to V Hermitian is equals to also identity, and yeah, and clearly my sigma 1 and my sigma is in this form, right? It's in this form with sigma 1 greater than or equals to sigma 2 and both being non-negative. So my sigma 2 here is, which is my second largest singular value, which is what has been asked in the question. It is 24 root 2, and I think it is the fourth option, 24 root 2. So your correct answer is option D. Okay, and I think with this we have come to the end of today's discussion, and I think you had a question, right?
Yes, actually, I had a question about our beamforming.
Okay, beamforming, huh?
Beamforming, like we are taking user one as actual
Desired user, yeah.
user two, but practically we will not be having such things. For example, I just wanted to check for an example of this, where we use such kind of application.
Okay, so yeah, this is, I mean, yeah, this is a very simplified setting. I mean, in general,
Yeah.
it's a very simplest case where you have just 2 users, but in general, there could be lot of interference. As I was telling in the context of like wireless cellular communication, when you have like adjacent cells, so you will have the interference from adjacent cells. So yeah, for that, I think you can, if you want to know more, you can refer to any textbook. The one, I think, the very common textbook, I think, Rappaport.
Okay,
I'm not sure if I spelled it correctly or not. So this is the standard textbook. There are multiple other textbooks as well. Proakis is there for digital communication, and so Andreas Goldsmith's books is there. Many books are there actually. So you can refer to any textbook if you want to know like the more generalized cases and so on. But yeah, so I'll try to, I mean, stick to the course
Yeah.
contents. That's why, I mean, I'm unable to
Yes.
do these things. But those are like definitely interesting exercises to explore. So yeah, and of course, I mean, the theory and practice is like totally entirely different things. You know, in theory we talk about a lot of things, a lot of approximations and all, but in practice, in practical, everything changes. So yeah,
Exactly.
yeah, yeah. So uh, yeah, so yeah, I think that's all I think I can say at this point. And okay, if there are any no more questions, then we can sign off for today, and we'll meet again on next Friday, 6 p.m.
Thank you. Thank you.
Okay, thank you.